Steinhauer here. Welcome back. We have been skipping around a little bit, but we are solidly now in chapter 23, which is a chapter on the death of stars, how stars die. We've already seen some of this, but this is more on the remnants that they leave behind. So we've already talked about white dwarfs. This is, again, the carbon-oxygen core of a low-mass star like the sun that has been left exposed when a star sloughed off its outer layers in a planetary nebula. And these things are roughly the size of the Earth, and you can see that here. A one solar mass, a white dwarf that has a mass of one solar mass, is almost exactly the same size as the Earth. Interestingly, and this is one of the weird things about white dwarfs, the more massive you make them, the smaller they get. And so the density goes way up as you make a white dwarf much more massive. So that's just an interesting factoid about the structure of a white dwarf, that they get smaller when you make them more massive. Now, we've already talked about this at some level. There is a fundamental limit to how massive you can make a white dwarf. And that's caused by the quantum mechanical fact that says that electrons cannot occupy the same quantum state. They cannot be in the same place at the same time at the same energy. And so what happens when you try to move atoms closer together? They must go to higher and higher energy levels. And what does that mean? It means that they're moving at faster and faster and faster speeds. And it was a guy by the name of Subrahman Chandrasekhar, probably the most brilliant theoretical astrophysicist of the 20th century, Indian-born, who derived this limit for the first time. And he realized that if you make a star more massive, eventually those electrons must get pushed into a state where they're trying to move faster than the speed of light, and that cannot happen. Nothing can move faster than the speed of light. And so he derived the limit for what that mass was at about 1.4 solar masses, and it's known as the Chandrasekhar mass limit today. And so, since nothing can move faster than the speed of light, that sets an upper limit for how massive you can make something supported by electron degeneracy, like white dwarfs. You cannot have a white dwarf that is more massive than 1.4 solar masses. So that's an interesting factoid about white dwarfs and about the limits of their mass. So this brings us to types of supernovae. We've already talked about one type of supernova. By the way, supernovae with an E on the end is the Latin. Supernova is a Latin word, and when you pluralize a word that ends with A, you put an E on the end instead of an S. Supernovas isn't wrong, but supernovae is the typical what people will say when you're talking about more than one supernova. So just a factoid about plurals of supernova. Anyway, we've already seen one of these types, right? A massive star at the end of its life. You have an iron core. That iron core undergoes photodisintegration. And the core collapses, and the entire star explodes. This is what's known as a type 2 supernova. This is a typical massive star at the end of its life, supernova, where the core, often called a core collapse supernova. And these are, again, among the brightest objects in the universe, but they don't all have the same amount of luminosity, right? The more massive the star you have, like 10 solar mass stars go supernova, as do 15 solar mass stars, as do 25 solar mass stars, as do 50 solar mass stars. And the more massive star you have, the more luminous that supernova is. Now, there's another type of supernova. In fact, there's more than one other type of supernova, but we're going to be interested in one other particular type of supernova in particular, and that's known as the type 1a supernova. Type 1a supernova, there is actually some controversy and some uncertainty about what the true progenitor of a type 1a supernova, meaning what is it that explodes? What is there before the explosion happens? We're pretty sure that it's a white dwarf. And imagine that you have a white dwarf that's sitting there that's close to the Chandrasekhar mass limit. Let's say it's 1.35 solar masses. And let's say that that white dwarf is in a binary system with another star. And let's say that that star becomes a red giant and becomes so big that it starts dumping matter onto the white dwarf. Well, we think in such a scenario, it's possible that the white dwarf can exceed the Chandrasekhar mass limit. And if that happens, it will, in fact, implode and then explode. And we think that this is what happens when you get a type 1a supernova. A white dwarf exceeds the Chandrasekhar mass limit, and the whole thing blows up in a spectacular way. Now, these are really interesting objects because they all happen for white dwarfs that have exactly the same mass, right? 1.4 solar masses. Every single one of them will be very close to the Chandrasekhar mass limit, will exceed the Chandrasekhar mass limit, and will explode. And so the question posed on this slide, will there be a large difference in the brightness of type 1a supernova? We expect that the answer to that question will be no. They all have the same mass when they explode. They should all have about the same luminosity. And that makes them extremely important. Why does it make them extremely important? Because they're very bright. Among the brightest things in the universe. These things are brighter than most type 2 supernovae, in fact. And they all have the same luminosity. What is it that we can determine if we know what a star's luminosity is just by measuring how bright it appears to us? We can get the distance to that object. Remember, brightness and luminosity and distance are things that are related. We can always measure the brightness of something. If we happen to know its luminosity too, it's a standard candle. And we can use standard candles to determine distances to things in astronomy. And this is going to be very important. We're going to come to a point in the next few weeks where we're talking about understanding the universe as a whole. And I'm going to say, remember those type 1a supernovae and how important they were to determining distances. And you're going to go, oh yeah, I remember that. That was important. They're going to be really important for helping us understand how the universe is structured and what it's like. So keep these type 1a supernovae in mind, and we'll come back to them later on in the class. Okay, great. What do you leave behind, though, in a type 2 supernova? Remember what happened in that type 2 supernova. You had an iron core, and you had that iron core exceed the Chandrasekhar mass limit. Photodisintegration happens. All those iron atoms get turned back into protons. All those protons combine with electrons to make neutrons, and those neutrons collapse down and form a giant ball of neutron degenerate matter that then bounces and the rest of the star explodes. So often it is the case that that core will survive the blast, and you will have an object there that is made almost entirely of neutrons. And what do we call such an object? Well, we call it a neutron star. And how big are they? Well, they have diameters of about 10 kilometers, or about the size of a small city, a moderate-sized city. What are their densities? This is mind-bogglingly dense material, because this is something that has mass more than the sun compressed down into a space the size of Rochester, right? This is atomic density. This is a density on the order of 10 to the 17 kilograms per cubic meter. Again, that's a 10 to the 17. That's a 1 with 17 zeros after it, right? This is nuclear density in an atom. You cannot get any denser than this and still have it be normal matter, right? Normally, when you have an atom, the nucleus is at the center of this atom, and you have an electron cloud. But the electron cloud is 5 orders of magnitude bigger than the nucleus itself, right? And so most of an atom is empty space, where you're a tiny little thing at the center and this giant electron cloud in which these electrons are buzzing around, occupying the vast majority of the space. Well, that all goes away in a neutron star. There are no electrons anymore. You basically have a giant neutron, a giant atomic nucleus the size of a large city, right? This thing has the density of the nucleus of an atom, except it's something that's more massive than the sun. This is as dense as you can get stuff and still have it be kind of regular matter. So you might remember we did this thought experiment with a white dwarf, right? What if you could land on the surface of a white dwarf and pick up a cubic centimeter, a teaspoonful of white dwarf material, and we found that that would weigh a metric ton? This stuff is a neutron star is way denser than a white dwarf. So let's ask the same question of a neutron star. What would a cubic centimeter of neutron star, 1 teaspoonful, weigh on Earth? Again, you couldn't actually land on this neutron star and pick it up. You wouldn't be able to pick it up anyway, but you'd be squished flat just getting anywhere near a neutron star anyway. Anyway, if you could though, what would its mass be? How much would it weigh? Okay, well, we can do this the same as before. Mass equals density times volume. We know that the density is 10 to the 17 kilograms per cubic meter. And now we need to, and we know that the volume is 1 cubic centimeter. We did this before. We need to multiply this by the number, by a number that has meters cubed on top and centimeters cubed on the bottom, so that these will cancel out. And we'll be left with kilograms. So we need to know how many cubic centimeters there are in a meter, in a cubic meter. We did this last time. There are 10 to the 2 or 100 centimeters in a cubic meter. There are 10 to the 2 cubed or 10 to the 6 cubic centimeter in a cubic meter. So I can take 10 to the 17 and divide it by 10 to the 6, and then I get the mass of this thing in kilograms. And so 10 to the 17 divided by 10 to the 6, again, this is easy. You can do this without a calculator. If you're dividing two numbers with just exponents, you can just subtract the exponents. 17 minus 6 is 11. This is 10 to the 11 kilograms. 10 to the 11 kilograms. That's a 1 with 11 zeros after it. This is 10 billion kilograms. This is roughly the mass of Mount Everest, all compressed down into the volume of a sugar cube. 1 cubic centimeter, a teaspoonful. 1 teaspoonful of neutron star has roughly the same mass as Mount Everest. So this is as dense as stuff gets. You can't get any denser than this. Okay, we'll come back in the next video and talk more about neutron stars and how we observe them and some interesting objects that we think, in fact, are neutron stars. See you then.